Okay, today we will see several examples regarding Faraday's law, and we will finish Faraday's law with the examples and in the next lesson we will see several examples on how to apply Maxwell equations, and from the next week we start a new topic, which is electromagnetic waves. Okay, let me see the problems. Okay. First, this is the problem. Okay. Let's read the problem. We have a square loop. Well, we have a square loop with the side of B, and which is placed in a magnetic field with magnetic flux density capital B. So these are the magnetic flux density lines, capital B, where capital B is equal to K by T. Okay, sorry. K multiplied by T, where K is constant, which is equal to 200 Tesla per second. And the normal of the surface of our loop, angle between the normal of surface of our loop and magnetic flux density is given as alpha. Okay. Okay, not alpha, here is written beta. Well, beta. And our loop is connected with the help of wires, is connected to two capacitors which are connected in series with capacitance of C1 and C2. C1 and C2 are given. So we need to find the voltage drop across capacitors V1 and V2. Okay. First of all, what we do? First of all, we need to find electric motive force due to the change of magnetic flux through our contour, through our loop. Well, okay, let me open a new page. I will write in a new page now. Electric motive force was equal to minus the phi over the T, where phi is magnetic flux through our contour, and phi is equal in our case. So phi is in general was equal to B ds, and in our case this integral becomes B multiplied by S multiplied by cosine beta. And if we write electric motive force will be equal to minus d the t. Okay, b as cosine beta, where b is equal to k multiplied by t. So minus again, so d over the t, b is k multiplied by t multiplied by s multiplied by cosine beta. And if we take a time derivative from this expression, we have that electric motive force will be equal to minus k multiplied by s multiplied by cosine beta. K multiplied by s multiplied by cosine beta. Or, okay, we can write the absolute value of electromotive force, and we have k is equal to 200. The constant k is equal to 200. S is equal to well, let me write here, s is equal to b squared, which is 0.01 squared and 10 to minus 4. S is equal to 10 to minus 4, 10 to minus 4, and okay, cosine beta, okay, let me write here again, cosine beta, which is okay, or let me write instead of beta, 30 degrees is equal to square root of 3 over 2. Okay, multiplied square root of 3 over 2. And if we compute the numeric value, what we get? 200 divided by 2 multiplied by 10 to minus 4 and multiplied by square root of 3. 0.0173 volts. Okay, let's double check. Multiplied by square root of 3 divided by 2. Okay, that's right, correct. We have found electric motive force. Now let's go to our problem and see. So our problem suggests following scheme. Our contour, in this case square contour, is connected with the help of wires to the capacitors C1 and C2. Now let's redraw our circuit, and what we have. If we redraw our circuit, we have electric motive force, which is connected two capacitors in series. So electric motive force, this is C1, this is C2. we have a voltage source here to which connected two capacitors in series. Now we need to find voltages across capacitor 1 and capacitor 2, V1 and V2. So we have the general formulation for the capacitance of capacitors is C is equal to Q over V, and because of the fact that our capacitors are connected in series, charges in our capacitors will be equal to Q, and the equivalent capacitance will be 1 over C1 plus 1 over C2 to the power of minus 1, which is equal to C1 and C2 over C1 plus C2. Okay, now we know the equivalent capacitance, and we know the voltage drop. So we know the voltage drop across equivalent capacitance, which is equal to exactly to electric motive force. Okay, we know voltage drop between these 2 points, and now we can write the expression for charge Q, which is equal to electric motive force multiplied by equivalent capacitance, and is equal to electric motive force by C1 by C2 over C1 plus C2. Okay, we know that charges are equal over the capacitors, and this is equal to Q1 and equal to Q2. Now we know the value of Q1 and Q2, and we easily can find the values of voltages across capacitors V1 and V2. So in order to find V1, we use Q1 over C1. So Q is equal to electric motive force C1 C2 over C1 plus C2 multiplied by C1. C1 and C1 simplifies. We have electric motive force multiplied by C2 over C1 plus C2. And similarly, the voltage drop across the capacitor 2 so don't confuse these two. Okay, similarly, voltage drop across capacitor 2 V2 is equal to Q2 over C2, which is electric motive force multiplied C1 multiplied C2 over C1 plus C2 over C2 equal C2 simplifies. We have electric motive force multiplied by C1 over C1 plus C2. Well, we found the voltage across capacitors C1 and C2. Now let's see the next example. Next example is more or less the same. However, capacitors are connected in parallel. Capacitors are connected in parallel. And what we have? We have again magnetic field with flux density B, which is given as again KT, and we have a square loop with the side of B, which is again 1 centimeters. Only the angle between the normal to our square loop and to the magnetic field lines, beta is 45 degree. Okay. We have again two wires going from the capacitor, from the loop, and these two wires are connected to the capacitors C1 and C2, so that C1 and C2 are connected in parallel. This is the first capacitor, and this is the second capacitor. This is C1. Now you need to find Q1 and Q2, which is very simple, very easy. Please, you have 3 minutes. Please try to solve by yourself. After 3 minutes, I will show how to solve. Okay, are you following? Are you solving? Well, Q1 and Q2. First of all, you try to find electric motive force. After that, due to the fact that capacitors are connected in parallel, voltage drop across capacitors is equal, V1 equal to V2, and with the equation which says C equal to Q over V, you find the charge of each capacitor. Okay, have you solved? Well, let me solve myself in that case. Again, electric motive force is equal to minus the phi over the t, and in our case the magnetic flux across our contour, across our loop, is b multiplied by s multiplied by cosine beta. B s cosine beta, and b is k by t. S is b squared. Cosine beta is cosine 45 cosine of 45 degree, and if we take a derivative from this expression with respect to time, we have k b squared, so k multiplied by b squared multiplied by cosine 45, and is equal to, the numeric value of this equal to k is 400 multiplied b is 10 to minus 2, b square is 10 to minus 4. Here b is 10 to minus 2 and b square is 10 to minus 4. Cosine 45 degree is square root of 2 over 2, and let's compute 400 multiplied 10 to minus 4 multiplied by square root of 2 divided by 2. Okay, multiplied by 400 multiplied by 10 to minus 4, 0 0.028 0.28 volt. Electric motive force equal to 0.028 volt or 28 millivolts. Now let's again we redraw our circuit. We draw the equivalent circuit of our previous circuit. This is the electric motive force, and here we have one capacitor and here we have another capacitor. Two capacitors are connected in parallel, so this is C1, this is C2. Okay, voltage across first capacitor is V1, voltage across second capacitor is V2. So from the picture we can say that as capacitors are connected in parallel, V1 is equal to V2, and from the other side we can see that V1 equal to electric motive force, and we find that voltage across both capacitors are equal and equal to electric motive force. And now we can find easily the charge in each capacitor. So the charge in the first capacitor will be C1 multiplied by V1, where C1 is equal to 1 microfarad. So 1 microfarad is 10 to minus 6 multiplied by V1. V1 is V1 is electromotive force, which is 0.028. So 2.8 10 to minus 3, yeah, or 10 to minus 2. Yes, 10 to minus 2. And we have 2.8 10 to minus 8 coulomb, or 28 nanocoulomb. And charge on the second capacitor Q2 is equal to, again, C2 V2, and C2 is equal to 2 microfarad to 10 to minus 6 farad, and V2 is again 2.8 2.8 10 to minus 2 is equal to 58 56 nanocoulomb. Okay, let's move to the next problem. The next problem is this, or yeah, let me copy this by part. So okay, okay, now what we have. We have a generic loop with the uh, surface equal to 100 centimeters square, and this loop has uh, 1000 turns. Okay, and this our loop is rotating in the with the frequency of 10 hertz in a magnetic field with the magnetic field intensity H equal to 10 to the power of 4 ampere per meter. So we need to find electric motive force and the maximum value of electric motive force and the maximum value of electric current if the uh, resistance of our loop is equal to 100 ohm. Okay, so let me draw. We have the magnetic magnetic field with magnetic flux density B, and we have a loop which is rotating in this field. So the angle between the axis of rotation and angle between the magnetic flux density lines is 90 degree, and the frequency of rotation omega is equal to 2pf. Here f is given as 1 hertz, 10 hertz, and we have omega equal to 20p radians per second. Okay, we need to find the maximum value of electric motive force. So again, the electric motive force is equal to minus the phi over the t, where phi is equal to b, without vector, b multiplied by s multiplied by cosine, let me say alpha. Due to the fact that our loop is rotating, this alpha will also change in time, and alpha will be equal to the uh, frequency omega multiplied by t. And what we have, we have phi equal to, no, wait, we don't know b. For b, we have the equation b equal to mu multiplied by h. Mu in our case equal to mu zero, because we are working in a free space or in the air, and b will be equal to mu zero by h. And well, phi equals to mu zero h s cosine omega t. Okay, and we found that magnetic flux through our loop, and electric motive force will be equal to minus the phi over the t. Instead of phi we put this expression, and we have minus d over the t of mu 0 h s cosine omega t. Okay, we need to take the derivative of this expression with respect to time. We go to a new page and we find that. For now, let me write here, and then I will erase. So electric motive force will be equal to mu 0 h s are constants, that's why they go out of the derivative h s, and derivative of cosine omega t is minus omega sine omega t. So omega sine omega t. Okay, we know numeric values of mu0, of h, of s, and of omega. And let's find the numeric value of electric motive force. Mu0 is magnetic permeability of empty space, and it was equal, if I'm not mistaken, it was equal to 4p multiplied by 10 to minus 7, or yeah, let me check. So magnetic. So electric motive force is equal to mu0 is 4 pi multiplied by 10 to minus 7 multiplied h was given as equal to 10 to the power 4, so 10 to 4 multiplied s was given as 100 centimeter squared is equal to, okay, 100 centimeter square is equal to 100, 10 to minus 4, 10 to minus 2, 10 to y parentheses, y brackets, s is equal to 10 to minus 2, and omega was equal to, omega we found is equal to 20p radians per second, 20p, and multiplied by sine omega t. Now, so electric motive force equal to, so 4 multiplied p multiplied 10 to minus 7 multiplied 10 to 4 multiplied 10 to minus 2 multiplied by 20 multiplied by p equals to 7.89, or better, we can write it as 7.9 10 to minus 3 sine omega t. Well, please pay attention in this equation of, so in this equation of electric motive force, I skipped the number of turns n. That's why we found electric motive force. Let's do this EMF prime, electric motive force prime. Electric motive force per one turn of our coil. So EMF prime, prime, prime. This is 7.9 multiplied 10 to minus 3 sine omega t volts per one turn of our coil. And total electric motive force will be number of turns multiplied by electric motive force per one turn. And this is equal, number of turns is in our case 1000 multiplied by 7.9 10 to minus 3, and okay, so 10 to minus 3 multiplied by sine omega t, and is equal to 7.9 sine omega t volts. Okay, and the maximum value of electric motive force. So we have that for electric motive force, we have this law. It means our electric motive force is harmonic, and it is changing with sinusoidal law, and the maximum value of electromotive force is 7.9 volts. And from this, we can find the maximum value of I, which is maximum value of electromotive force divided by R. From here, I0, so the R was given as 100 ohm. Okay, 7.9 over 100 and is equal to 79 milliampere. Okay, the maximum current which flows through our circuit or through our loop is 79 milliampere, and maximum value of electric motive force is 7.9 volt. Okay, have a rest of 10 minutes, and after that we will continue our lesson.